Okay, so we will continue our discussion now regarding analysis of variance. Okay, so if we are comparing between more than two sets of data, then we cannot use t-tests, but rather we have to use the analysis of variance. Okay, comparing between two sets of data, meaning that we are comparing, for example, between two factors, or we are comparing between two treatments. Sorry, more than two factors or more than two treatments. Okay. So all of this, when we are in this situation, then we should be using analysis of variance as opposed to multiple t-tests. Okay. However, analysis of variance only determines whether there are significant differences between the sets of data, but it does not determine which set of data is different from another set of data. Okay. Okay, so when do we use it? When we want to compare more than two groups, okay, or two sets of data. For example, if you have one control and two treatments, okay, so these are considered as more than two sets of data because the control itself is a set of data, okay, plus two treatments. So in this situation, we are comparing between three sets of data. Or for example, if you do not have control or the control is part of your treatment, then you have four treatments, then meaning that you are comparing between four sets of data. Okay, so the hypothesis, okay, for analysis of variance, okay, for one-way analysis of variance is the H naught, that is the null hypothesis, is mu1 equals to mu2 equals to mu3 equals to mu4, or if you have more than four sets of data, then it is like equals to mu5, etc., etc. Okay, or the alternate hypothesis is mu I, that is any of these 1, 2, 3, 4 means, okay, differs in at least one treatment. Okay, so meaning that if we there is enough proof, so we will reject the alternate hypothesis and we will accept the null hypothesis. Or if you have enough proof to you do not have enough proof to accept the null hypothesis, then we will accept the alternate hypothesis. Okay, so the interpretation is based on the F value. Okay, but however, usually now we only look at the probability values. Okay, so for ANOVA, we may use one factor or one-way ANOVA or two-way ANOVA. One-way ANOVA if we only have one factor. Two-way ANOVA if we have more than one factor, that is two factors or more. Okay, for comparison, then we can use a two-way ANOVA. Okay. Okay, as I mentioned just now, okay, ANOVA only determines that there are at least one mean or one set of data that is different, significantly different than another set of data. That's all. But it does not determine which set of data is different, significantly different from which set of data. For example, if you have four sets of data A, B, C, and D, okay, if there are at least one set of data which is significantly different than the other set of data, then ANOVA will say that, okay, will give a result of there is a significant difference, okay, between the sets of data. But which set of data is different from which set of data? For example, if is A different, significantly different than B, or is A significantly different than C, or is B significantly different from D, those information we will not be able to get from ANOVA. So if ANOVA tells us, okay, that there is a significant difference, okay, between the means, then in order for us to determine which set of data is different from which set of data, then we need to do a multiple means comparison test. Okay, so we use this when we need to compare between means. Okay, and there are several types of MMCTs. Okay, among the more popular ones commonly used is in food science, that is Tukey's, Fisher LST, and Duncan tests. Okay, in food science technology, we usually commonly use Duncan, but it is okay. It is you can use any of these three or any other. It's up to you. Okay, and during software usage, okay, ANOVA, you have to remember this, ANOVA overrules MMCT, because in marginal situation where, for example, the difference significant, the probability is marginal to 0.05, then there is a possibility that even though the ANOVA result is not significantly different, but when you do your MMCT, then you can see that there is a significant difference. In this kind of situation, always refer to the ANOVA first. Okay, always refer to the ANOVA because ANOVA overrules MMCT. Okay, so in practice, it is always better to check the ANOVA first, and if the ANOVA is not significant, you do not have to look at the MMCT. Okay, but if the ANOVA is significant, then only you look at your MMCT results. Okay, so this is an example, okay, of a one-way ANOVA output. Okay, this is using SPSS. Okay, so in this case, we can see that the probability is very, very low. So meaning that it is lesser than 0.05. If you were to take that our confidence of interval is 95%, then this is less than 0.05 over here. Okay, so it is significantly different. Then only we look at the post hoc test or the multiple means comparison test. Okay, in this case we are using Duncan. Okay, and then this is what we get. So we know that among the three means that we are comparing, you can see that there are three means, three sets of data. You can also look at this number, degree of freedom, meaning that there are we are comparing between three sets of data. Okay, so there are significant differences, meaning that at least one mean is different from the other. Okay, but which one we do not know. Then we do the multiple means comparison test, the Duncan test, and then the software will give us, okay, the output like this, where any means that is within the same column is not significantly different. In this case, you can see that each of the mean is in different column. So meaning that each of the mean is significantly different from the other. Okay, so that is the one-way ANOVA. Okay, so for a two-way ANOVA, if you are dealing with more than one factor, okay, then it is advisable to use a two-way ANOVA. Okay, to use a two-way ANOVA, okay, the hypothesis, okay, is slightly different. Okay, where, okay, for example, in a one-way ANOVA, okay, one-way ANOVA, then the hypothesis is like this. Okay, we have the H naught. Okay, okay, the H naught. Okay, hypothesis. Okay, meaning that, for example, if we take it as a mu1, okay, is equals to mu2 equals to mu3, for example, and for the alternate hypothesis, then we have at least, okay, one mean is significantly different. Okay, however, for a two-way ANOVA, a two-way ANOVA, okay, so the null hypothesis will be Okay, assuming that we have two factors. Okay, just put it over here. Okay, two factors. Okay, so okay, the effects. Okay, okay, so kalau untuk two-way ANOVA, so dia ni sebab. Okay, kita akan ada hipotesis yang pertama. Okay, is that the factors, that the means, okay, the means of observations grouped by one factor are the same. And for our second hypothesis, because we have two factors, then okay, the means of observation grouped together, okay, by okay, the other factor are the same, or we have another. Okay, for the third hypothesis is that okay, there are no interactions between the two factors. Okay, so these are our hypothesis for a two-way ANOVA. If you can see that the hypothesis, okay, is different, okay, from between the one-way ANOVA and the two-way ANOVA. Okay. Okay, so when we have two factors or more, then it is advisable to do a two-way ANOVA so that you can determine objectively the effects of each factor. Okay, the effect of each factor, and also you will be able to determine whether there are significant interactive effects or significant interactions between the two factors. And it is better than a multiple one-way ANOVA, because if you are doing a multiple one-way ANOVA, then you will only able to determine the effect of the two factors individually, and it will be difficult for you to determine whether there are significant interactions between the two factors or not. Okay. Okay, so when we are doing a two-factor ANOVA analysis, then I would suggest to do a two-step analysis. Okay, this is according to Montgomery, 1991. Okay, the first is to do a two-way ANOVA. Okay, according to what we have discussed just now. Okay, so by using a two-way ANOVA, okay, we will be using this set of hypotheses. Okay, so from the first hypothesis, we will be able to determine whether the first factor, okay, whether there are significant effects of the first factor. For the second hypothesis, whether there are significant effects of the second factor, okay, and then okay, whether there are significant interaction effects, okay, between the two factors. And then in order for us to after we have done this, we can also do a multiple means comparison test, okay, to determine whether which of the different levels or the different levels of the first factor are the same or significantly different, similar to the second factor. And then for the interaction, okay, in order for us to explain the interaction, then it is easier for us to do a one-way ANOVA and also a multiple means comparison test, and then we can describe the interaction between the two factors. Okay.